All right, so our topic tonight, and I do apologize that this is a lecture and not a debate. I'm going to discuss the debate thing later on. But our topic tonight is the use of animals in science and research. So probably the first thing we should do is talk about how animals are used in science and research. And in point of fact, there are about 9 different ways that animals are used in science in general. And the first 2 ways are really the only 2 ways that I focus on, okay? And that's the use of animals as models for human disease and the use of animals to test new drugs. Now, what these 2 ways have in common is that the scientific community asserts that these are predictive models. And that's really what tonight's lecture is going to be about. It's going to be about prediction, what that means, what that doesn't mean, and so on and so forth. So the position that I take and that my group takes, Americans for Medical Advancement, the position that we take is that numbers 1 and 2 are not scientifically viable. Okay, animals cannot predict human response to drugs and disease. However, there are 7 other ways that animals are used in science, and all of these are scientifically viable. Okay, now there may be some of you here tonight who have issues ethically with the way animals are used. Oh, for example, as spare parts. An example of using animals as spare parts would be to harvest the aortic valve from a pig and then implant it into a human being that has aortic valvular disease. Okay? Now, some of you may have ethical problems with that, but scientifically it works. Matter of fact, it works really well. So one thing that I hope you appreciate even early on in this lecture is that there are 2 aspects to the animals in research controversy. Okay? One is the ethical aspect. You know, should we be doing this? Okay? It's like abortion. Should we be doing abortion? A very ethically contentious issue, at least in the US. The second issue is scientific. Does the animal model do what it is claimed by the scientific community to do? Okay? So, using animals as spare parts, the scientific community claims that the aortic valve from a pig can be placed into a human being, and they're right. It can. It works really well. So to get back to the abortion example, it's one thing to say, is abortion ethical? It's another thing to say, is abortion medically feasible? Well, as it turns out, abortion is medically feasible, okay? But there are ethical issues and there are scientific issues. And tonight, we're going to draw a great big line between the 2. I'm not here to talk about ethics. I am only here to talk about science. So, numbers 3 through 9 are scientifically viable. You can use animals as factories. For example, the production of insulin is a historical example of how animals were used as factories. You can use animals to study basic physiological processes, for example, the homeobox. You can dissect animals. They're heuristic. If you want to cure chihuahuas of cancer, I suggest you study chihuahuas. And then you can use animals just to generate more knowledge. Okay, scientifically, these are viable. How many of you here tonight have a science background? Oh, good, good. Okay, this slide is for you. I will let you read the slide, since this is my second lecture of the day. Okay, so the scientific basis of our position can really be summarized in this slide. And it can furthermore be summarized by saying that living complex systems have evolved over time. So the theory behind the empirical data, would be the fact that you cannot extrapolate results between complex systems, okay? And evolutionary biology explains why the initial conditions of two complex systems are so different and why they are so important. Now, for the scientists in the audience, after I finish my little lecture, if you want me to talk more about complexity and complexity science, I am happy to do that. But right now, I'm going to show a Far Side cartoon. So this is one dog in the car talking to the other dog on the lawn, and the dog in the car says, "Ha ha ha, Biff. Guess what? After we go to the drugstore and the post office, I'm going to the vet's to get tutored." Yeah, I don't think he's going to get tutored. I don't think that's what he's going to do. But words are important, and the definition of words are very important, especially in science. So we're going to talk a little bit about what the word predict means in science. Now, this is from a textbook titled Animal Models in Toxicology from 2007. And let's just read this. It says, biomedical science's use of animals as models is to help understand and predict response in humans in toxicology and pharmacology. That's pretty straightforward, okay? And that means exactly what it looks like it means. The GAD goes on, by and large, animals have worked exceptionally well as predictive models for humans. Animals have been used as models for centuries to predict what chemicals and environmental factors would do to humans. The use of animals as predictors of potentially ill effects has grown since that time. Blah, blah, blah. You can read the rest of it. Again, there is nothing subtle about this passage, okay? In fact, animal models are used to predict human response to drugs and disease. Now, there's other ways that they're used, okay? And most of those ways are scientifically viable. But what I frequently hear from the animal experimentation community is, oh, well, we don't use animals to predict human response to drugs and disease. Well, yes, actually you do. Maybe your lab doesn't do that, but there are a lot of labs around the country, especially in the pharmaceutical industry, as exemplified by this quote from this textbook, that do exactly that. So what does the word prediction mean in science? Well, as it turns out, it actually means a little bit different thing in the hard sciences of physics and chemistry than it does in the biological sciences. But here's a reasonable definition. It's actually from Wikipedia, but I swear it's the best definition I found. It says, a prediction is a statement or claim that a particular event will occur in the future, and note in the future, in more certain terms than a forecast. In a scientific context, a prediction is a rigorous, often quantitative, and again, that's important, that's why it's in red, quantitative statement forecasting what will happen under specific conditions, okay? In the hard sciences of chemistry and physics, you deal with what are called laws, okay? And there are no violations of those laws. Boyle's gas law is inviolate, all right? But in the biological sciences, life is much more based on statistics, okay? We don't really have in biology laws like you have in chemistry and physics, okay? Now we could get into a very long and pointless debate about what laws are and whether we have them in biology and yada, yada, yada. That's not the point. Probably 98% of the scientific community will agree with me that we don't have laws in biology. So when we want to study a phenomenon, all right, we have to use statistics. And statistics were a tremendous invention, and they continue to serve society well, despite what Mark Twain said. Now, this is a little 2x2 table, and most science majors study this table in their first year of science courses in college. And one thing that this table allows us to do is test a test, okay? So let's say that you come to see me as your physician, and I say, wow, I think you might have lung cancer. Okay, what I want to do is a test to see whether or not you really have lung cancer. So I want to give you a really good test. I don't want to give you a test that gets it wrong more often than it gets it right. And by studying positive predictive value and negative predictive value and filling in the little boxes on this 2x2 table, I can judge whether the chest x-ray is a good way to diagnose lung cancer, or a pulmonary biopsy is a good way to diagnose lung cancer, and so on and so on. Now, this little 2x2 table can be used not only to test a test, but to test just about anything that has a correct answer and that you're trying to derive the correct answer indirectly. So if you want to know if drug-sniffing dogs at the airport are a good way to find drugs, you can collect data and you can put it in this little 2x2 table, and you can come to a conclusion that, wow, these dogs are really, really good, let's keep them, or wow, these dogs are really bad, this modality doesn't work, and so on and so on. And lo and behold, we have done that. We have tested drugs on humans, or we have given them to humans, I should say, and then gone back and retrospectively tested them on animals, and here's what we found. So I think this data comes from the pharmaceutical industry. In fact, I'm positive it does. And they looked at 6 drugs, and they looked at all the side effects, and they found that animals and humans shared 22 side effects. The animals incorrectly identified 48 side effects that did not show up in humans, and the animals missed 20 side effects that did come up in humans. Now, what that gives us is a positive predictive value of 31%. That's not what you want when you go to your doctor, okay? When you go to your doctor, what you want is a test that has a positive predictive value in the 0.9 range, okay? Either a positive predictive value of 0.9 or a negative predictive value of 0.9. But yeah, 31%, that's right around what you would get with random guessing, okay? In other words, animal models, according to this study, are not predictive. Now, this is one study. We also have in science a difference between what are called anecdotes and what are called examples. An anecdote is, my mother went for a walk in the rain and it cured her rheumatism. An example is, I gave antibiotics to a patient with pneumonia and he got better. The difference between those two things is that there is a vast scientific literature of people who got antibiotics and were cured of their infection, whereas your Aunt Lulu's rheumatism is a once-in-a-lifetime phenomenon, okay? This comparative drug study is one of many that is in the scientific literature, and all of them have a sensitivity and positive predictive value in the same range as the one you see on the screen. So it's going to be pretty difficult to spin this into A, being an anecdote, and B, spinning this to say, oh, well, you know, this is just one study. There must be hundreds of other studies out there that show that animal models are predictive. Nope, there aren't. Not in drug testing and not in disease research. But sometimes you don't need the fancy little statistics to figure out what the PPV is. Right now, as of today, somewhere around 100 vaccines have been shown to protect monkeys from HIV or SIV or SHIV, okay? Every single one of them has failed to protect humans from HIV. Okay, when 0 is the numerator, yeah, it doesn't really matter what that denominator is. The same is true of neuroprotectant drugs. Actually, thousands have now been tested in animals and shown to be effective. 0 have been effective in humans. Okay? Now, even if an HIV vaccine comes out tomorrow, and I hope it does, and even if it was 100% dependent on animal-based research, you still cannot say that the monkey model of HIV is predictive, okay? Because predictive means I forecast the answer 20, 30, 40 times in a row, and I got it right about 95% of the time. Okay, that's what these little statistics let us do. Just getting the answer right once, nobody cares. And there's another way to show that animal models are not predictive. This is a graph. On the x-axis, we have what's called bioavailability in animals. And on the y-axis, we have bioavailability in humans. Now, in drug development, we try to figure out what the absorption of a drug is and what the distribution of a drug is. Really and truly, no one cares what the absorption is and no one cares what the distribution is. What they care about is the bioavailability. And what that means is how much of the drug gets to the target, okay? So I don't care if it's 100% absorbed and 1% distributed or vice versa or whatever. What I want to know is how much of that drug goes to the target. So the little squares are the results of testing these drugs in primates. Then the circles are rodents and the triangles are dogs. And for those of you who don't have a science background, we have a very fancy science name for this pattern on the graph. It's called a shotgun pattern, also known as a scattergram. Okay, and what this means is that there's absolutely no correlation between what the drug did in the primate, rodent, or dog versus what it did in the humans. And again, folks, I can stand up here all night and show you slide after slide after slide. Okay, the bottom line is animal models are not predictive for drug development or for the study of human disease. Okay, they can be successfully used for a lot of other things, but those two things, they fail. Speaking of other ways that animals can be used in research, in my little table, well, here, I have my little table right here. Wasn't that smart of me to put my little table in? Okay, so numbers 1 and 2, we say it just flat out doesn't work. Okay, if you're claiming that this animal model is predictive for humans in terms of disease and drug response, you're looking at data that I don't have access to.